Thank you very much for the invitation. Right, my talk will be, in some sense, a sort of special case of Hélène and O's talk from Monday, so I'm going to look at a tower of varieties and show that the direct limit of their cohomology vanishes above the middle degree, but the tower will be slightly different, so the transition morphisms will not be taking just piece power roots. And I guess the other difference is that I'll use p-adic geometry rather than the direct proof that Hélène and O talked about. Okay, so I want to start with some motivation that actually goes beyond the setting of algebraic varieties. I want to talk about completed cohomology of locally symmetric spaces. So this is a motivation for this for why you would be interested in this particular tower. So I start with a connected reductive group, G over Q, and attached to it, I look at the symmetric space for the real points of the group. So for this Lie group, and you can define this just by the quotient of the real points of the group by a maximal compact subgroup, and also by a torus part that is the connected component of the identity inside the R points of the maximal Q-split torus in the center of the group. Okay, it won't matter, the precise definition won't matter too much. So for instance, you can just think that the group G is semi-simple, and then the symmetric space is just G of R mod K infinity. And if I assume, so I'm interested in locally symmetric spaces, so quotients of this symmetric space by certain arithmetic subgroups, and the specific arithmetic subgroups that I'll be interested in are congruent subgroups. So for this, I have to assume that we have an integral model of G. And I'm going to then look at subgroups of G of Q that are cut out from the Z points by congruences. I'll give you examples. And then, so the real points of the group act on X, and gamma is a subgroup of that, so it acts on X. And if it's sufficiently small, the quotient is real manifold. So let's assume that gamma is sufficiently small, and this can be made precise, but I want to do it right now. We're going to define X gamma to be the quotient X mod gamma, and this is a locally symmetric space for G. And it's a pretty nice space. It's a smooth, orientable, real manifold, and also has a Riemannian structure. And two examples to keep in mind that show sort of there's dichotomy in terms of, well, how accessible this space can be to algebraic geometry. So one is you can take G to be the group SL2 over Q, and then X can be identified with hyperbolic 2 space with the upper half plane endowed with the hyperbolic metric. And sort of the SL2R is the group of holomorphic isometries of this. And the X gammas are modular curves thought of as Riemann surfaces. And more generally, you can have Shimura varieties. So these are higher dimensional generalizations of modular curves. One example is if G is, say, I can take similitudes or not, but let me take GSP2G for some integer G, and that is at least 1, and then the corresponding X gammas are Siegel modular varieties. which are moduli spaces of principally polarized abelian varieties with some level structure determined by gamma. And to be really precise, maybe it's better to, so there's a definition of these locally symmetric spaces that is adelic, and it's sort of the two match up to taking looking at disjoint unions. So I want to just pretend that I can just take this quotient by a subgroup. Okay, so that's one example. And then more generally, you have Shimura varieties whenever this symmetric space, which is a priori just a Riemannian symmetric space, is actually a Hermitian symmetric domain, so in particular has a complex structure. Then the locally symmetric spaces X gamma are also algebraic varieties, and they're called Shimura varieties. So maybe I'll just say that when X is a Hermitian symmetric domain, it can be identified with a conjugacy class, GR conjugacy class of homomorphisms from so-called Deligne torus, which is the restriction of scalars from C to R of GM, which is the Tanakian group for the category of real Hodge structures, to GR, satisfying certain axioms. And in that case, GX is called the Shimura datum. And the X gammas are Shimura varieties. They are in particular complex algebraic varieties, but in fact they have models over number fields such as Q, such as happens in the case of modular curves sometimes. So X gammas are Shimura varieties. So for the purpose of the talk, you actually only need to, you can just think of the case of SL2 over Q, and hopefully even that in that case I'll say something that's somewhat interesting. Or you can think about Siegel modular varieties, and then I'll state the precise theorem for which Shimura varieties we can prove something. But I want to say there's also a non-example, and which is where these locally symmetric spaces don't have an algebraic structure, and that is when G is defined by taking V restriction of scalars of SL2 from some extension of Q. So I can look at a quadratic extension, and if I take a real quadratic extension, it's almost the same, so you still eventually get a Shimura variety, but, well, you still get a Shimura variety, but if I take F to be imaginary quadratic, you can just check from the definition of the symmetric space that I gave up there that it's going to be a real manifold of dimension 3. Turns out it can be identified with hyperbolic 3 space, and the X gammas are arithmetic hyperbolic 3 manifolds. This is what they're called. So together with metric, and the X gammas are. But in any case, both in case 1 and 2, you can talk about the Betty cohomology. So whenever I write cohomology and I don't say what kind, I'm going to think about Betty. And then I can take either usual or compactly supported cohomology of these spaces, which are all going to be real manifolds. And if I take the cohomology with complex coefficients, this can be described in terms of automorphic forms for G. So that's one reason you might be interested in these particular spaces, is that their Betty cohomology can be related to automorphic forms for the group G. So they play an important role in the Langlands program. And another thing is that, well, you don't necessarily have to look at cohomology with characteristic 0 coefficients, but you can also look at cohomology with torsion coefficients. And So no matter what, if you vary your gamma, you get a tower of locally symmetric spaces, and the transition maps between them are finite-étale. So you always have sort of a tower, and you can study cohomology in that tower. So what I'm going to do is I'm going to take for every m greater than or equal to 1, I'm going to define a specific congruent subgroup that's deeper than whatever gamma that we start with. So gamma p to the m is going to be defined to be all those g in gamma such that g is congruent to the identity. So I impose extra conditions modulo p to the m, extra congruence conditions. So I guess in the first example, you could look at SL2Z. That's not quite going to give you a Riemann surface. You need to take some congruent subgroup in there, but then you can sort of, make it deeper and deeper. And there's the following notion that's due to Emerton, which is this completed cohomology. So H tilde I of ZP, and I can take either usual or compactly supported cohomology, and it's just defined as, well, basically you want to take cohomology of the spaces in the tower with torsion coefficients, and then you also want to go up the tower. And the sort of right way to do this is first you go up the tower, take a direct limit over m, go to deeper and deeper levels, and again either usual or compactly supported Betti cohomology, and then you want to take these kinds of coefficients and take an inverse limit over n. And this you should think of as sort of, this is the best definition that we have for p-adic automorphic forms for a general connected reductive group. And I guess that's the motivation behind this definition. And this space actually has more structure. It's sort of can be studied using methods from representation theory, but we're not going to care about that. I'm just going to say that you should think of this as a space of p-adic automorphic forms. And one thing is that it really is different from just taking cohomology with characteristic zero coefficients, because there can exist torsion in the cohomology, or there can exist, it amounts to the same thing, classes in here that don't lift to characteristic zero. And in fact, there are even conjectures about how much torsion there can be, and sort of, well, can contain so-called torsion classes, which for my purposes, I just think of these as classes that don't lift to characteristic zero. It's a short exact sequence on sheaves that, and you take the long exact sequence on cohomology and relate that.
So this is kind of when you do inverse limit to define kind of the cohomology, usually there is a question about lim 1. Is it zero in this case? Or?
I don't know if lim 1 is zero or not.
You just take the naive limit.
Yeah, it's just the naive limit, and that's their definition. In fact, for our purposes, we're just going to study sort of, we can forget about this, just like in Hélène and O's talk, and in fact, you can just study the cohomology with FP coefficients. But I guess the reason I define it like this is just because this is something that is sort of important to understand in the Langlands program. And I guess sort of it, kind of thinking about this space is what motivated conjecture about cohomological dimension. So there exists a conjecture about completed cohomology. In fact, well, their conjecture, I'm not going to state it here. It's rather difficult to state, and it's going to take me outside the scope, but it's in a survey article written by Caligari and Emerton. In fact, it's phrased in terms of homology and Borel-Moore homology. But this conjecture is, well, motivated by sort of heuristics coming from the Piatic-Langlands program on one hand. On the other hand, which is equivalent to the Leopold conjecture when G is a torus, so it's a generalization, well, kind of extension to these locally symmetric spaces for groups that are not abelian. And this conjecture, in general, will predict that cohomology above a certain degree in this kind of tower of locally symmetric spaces vanishes. And it's for both usual cohomology and for compactly supported cohomology. They predict that both will vanish. In the case of Shimura varieties, so when X gamma is a Shimura variety, the conjecture implies that the cohomology will vanish above the middle degree. Maybe I'll move to the next board. That H tilde I, either usual or compactly supported, with ZP coefficients is 0 for I greater than dimension over C of the Shimura variety, which I think, yeah, I'm just going to denote it by D from now on. Okay, and this kind of vanishing for dimension reasons is going to be true whenever I is greater than 2D. And one toy model, it's really a very trivial example, but that can show this kind of vanishing in a tower, is where you look at, and you don't necessarily need to have an algebraic variety, you can look at S1 and the covering map of degree P, so Galois with Galois group Z mod PZ, you can look at this kind of tower, and then in this case, H0 completed, doesn't matter whether it's usual or compactly supported because the space is compact. In degree 0, you get ZP, but in degree 1, you get 0, just because whatever class, the class that generates degree 1 will just become infinitely p-divisible as you go up the tower. And another just remark is that you can always recover cohomology at finite level from completed cohomology via the Hochschild-Serre spectral sequence. So that relates completed cohomology, take continuous group cohomology with coefficients in completed cohomology that gives you a spectral sequence that computes cohomology at finite level. So Hochschild-Serre spectral sequence computes homology at finite level.
It's clear with total coefficients, but when you take the inverse limit, then my question about Limois could play a role, because if you don't have such a thing and you have the bad definition of continuous cohomology, you don't have, it shouldn't work.
Yes, I think, so the Hochschild-Serre spectral sequence should work also in the inverse limit, but I'm not going to use that. So if you prefer, you can just work with torsion coefficients.
Okay, you claim that it works.
I claim that it works, but I also claim that for simplicity, you can forget about taking the inverse limit. Computes cohomology at finite level. What you see is the continuous group cohomology of ZP. So it's just another way to see that, well, the cohomological dimension of CP is 1. So it contributes, will give you cohomology in degrees 0 and 1. The reason I'm doing this toy example is just because this is going to come up, the continuous group cohomology of ZP, which you can also compute via Kosul complex, is going to come up later in the theorem that we're trying to prove. And I guess another thing is that I mentioned a connection with Leopold's conjecture, and that can be seen in a paper of Hill, where you analyze this example using, so you analyze this kind of situation, but you also have to think about the exponential map and think about what these locally symmetric spaces for tori look like. But it's an exercise to see the connection. Okay, so what I want to do now is state the main result. So the first thing is a theorem of Schulze, which is in his 2014 ICM. Well, actually, so he mentions it there, but maybe in the case of Shimura varieties, it's proved in his torsion article in 2013. And so there he looks at the case where G and X, so from now on, I forget about general locally symmetric spaces. I only think about the case where you have a Shimura variety. So G and X is a Shimura datum. And I'm going to assume that it's a Shimura datum of Hodge type. So what this means is that it admits an embedding into the Siegel datum. Into some Siegel datum. So some GSP2G for some G together with the Siegel upper and lower half spaces. But for simplicity, you really can think about, say, modular curve or Siegel modular varieties. Okay, then this theorem is true. First, so the way that he proves it for completed cohomology, but with compact support. This is 0 for I greater than D. Okay, so I guess more recently, you've realized you can also study these kinds of towers of Shimura varieties where you don't have to go to full infinite level at P. So you consider some sort of partial level structure at P. It's not full infinite level at P. So what I mean by this is I can try and state this as the following. So this will have two parts. The reason I'm stating this in two parts is that the first part is already publicly available, so on the archive. So this is joint work with Dan Gulota, Chi-Yoon Su, Christian Johansson, Lucia Motz, Emmanuel Reinecke, and Shengqi Shi. This was a project at the 2017 Arizona Winter School. So if, it's slightly, what we prove is slightly more general than this, but for simplicity, I'll state it like this. So if G is GSP2G for some G at least 1, and I consider the level gamma 1 to be given by those G and gamma where I impose the condition that G is congruent to, well, you can write down symplectic matrices by like 2 by 2 blocks of G by G matrices, and I want it to look like this, modulo P to the M. And I define the limit HI tilde compactly supported ZP gamma 1, inverse limit with respect to M, direct limit HI X gamma 1 P to the M compactly supported with Z mod P to the M Z coefficients. So I define this version. Then this is equal to 0 above the middle degree. And in some sense, this recovers Schulz's theorem at infinite level because I can start with any base level that I want. So by taking a direct limit over those, I can recover also theorem 1. But so we've been thinking about how to generalize this, and the following is work in progress with Dan Galata and Christian Johansson. And it seems like, well, for now it seems like the best statement we can prove is that if Gx is a Shimura datum of Hodge type, so anything that admits an embedding into the Siegel datum, and such that the group, so this is sort of the big restriction that we cannot get rid of. We want the base change of our group to QP to be a split group. And then I can define a sort of pro-P Iwahori subgroup of level M, so pre-image in, say, G of ZP of n z mod p to the m z inside G z mod p to the m z, where this is the unipotent radical of a choice of Borel. And I take this kind of level gamma 1, which is now the intersection of what I started with this Iwahori, pro-P Iwahori, then also with the same definition of completed cohomology, you get that this is 0 for I greater than D, dimension of the Shimura variety. Okay, and I guess one thing to say is that this conjecture of Caligari and Emerton, so there's some related conjecture of Hida for the sort of so-called ordinary completed cohomology, and a conjecture of Urban for eigenvarieties, and it's possible that, you know, well, if you define this kind of level, this is exactly the level that you consider to define ordinary completed cohomology or to study eigenvarieties. So it may be that this may have something to say about these conjectures, but it's not clear yet because it's not the full conjecture, it's just this vanishing above the middle degree. So I said this Caligari-Emerton conjecture implies the statement that cohomology should vanish, but their conjectures actually says a little bit more. It's more complicated to state the full thing. All right, so that's the main result that I want to talk about. And I want to make some remarks about it before I say something about the idea of the proof. So remarks are that both these theorems use p-adic geometry, but they don't use automorphic methods. So in some sense, well, they use kind of only p-adic geometry. So you can again ask whether there exists a direct geometric proof. And I should say that by contrast, there are also vanishing theorems for Shimura varieties where you're looking at just the finite level cohomology, and then you have to also use sort of automorphic methods. In particular, you have to use a Hecke action, and then if you pick out sort of a sufficiently generic system of Hecke eigenvalues, you can prove similar theorems at finite level. But those are sort of really different in nature because those do use some information about automorphic forms. Otherwise, the theorems wouldn't even be true. Whereas this is purely geometric.
Is it necessary to take the inverse limit from the result we want? That is, you say that some inverse limit of the cohomology coefficient until the m is 0. Is it true that before limit?
Yeah, it's true. In fact, that's what we're going to prove, that the cohomology with FP coefficients is 0. And then you can, using that, you prove that cohomology with Z mod P to the MZ coefficients is 0, and then also in the limit.
Theorem is stronger.
Okay, so in fact you just stated it like this because people use it. Okay.
Yes, I don't know. Maybe, sorry. Yeah, maybe that wasn't the best choice to state it like this. But okay, but so the other remark that I wanted to make is that theorem 1 is also true for usual cohomology. So in the theorems, I always had compactly supported cohomology, but theorem 1 is also true for the usual completed cohomology of the Shimura variety. But theorem 2 is not. And the way that that I know how to, I can imagine how to prove theorem 1 and to see that theorem 2 is false is to look at the cohomology of the boundary. Sort of use an excision sequence, say an excision distinguished triangle that relates compactly supported usual cohomology and cohomology on the boundary. And you can do this even on the level of real manifolds. So you don't necessarily need to know that you have a Shimura variety. You can understand the cohomology of the boundary in terms of Levy subgroups of G, and then you can see how that behaves in towers. And so in particular, if you try to understand the cohomology of the boundary in the setting of theorem 2, you're going to see that there's some piece that you can never kill in the tower. It doesn't become P divisible as you go up the tower. And yeah, I can sort of just do that using the so-called Borel-Serre compactification, which is a compactification of the locally symmetric space just as a real manifold with corners. Okay. But, right, and somehow this is what makes theorem 2 interesting, is that because so compactly supported cohomology vanishes above the middle degree, but usual cohomology doesn't vanish, you can relate usual cohomology to the cohomology of the boundary, and there's an application to the Langlands program to construction of Galois representations for locally symmetric spaces. But don't want to say more about this now. Just say that this is what makes one reason why this theorem 2 is interesting. And another thing that I wanted to say is that there should also be some Shimura varieties for which the group is not split at P, for which theorem 2 holds. But they're sort of, I don't know, kind of, you can do some cases just by hand, but it's unclear how to do it in general when you don't have a split group. And I want at the end to give you an example where sort of the method that I'm going to describe in the rest of the talk fails. And okay, I haven't written this up, so I don't know, I can't say 100% as a theorem, but I think that there are some Shimura varieties, such as Harris-Taylor type Shimura varieties, where the theorem also works. So that's why maybe this is it would be nice to have another proof to see if that is more general. Okay, so what I want to do now is just give you sort of the idea of the proof, and for that I'm just going to discuss modular curves, because I just want to give you a hint of sort of what's happening geometrically. I think it's already you can see something in the case of modular curves. So this is the case where, well, you can look at, say, GSP2 is isomorphic to GL2. So it's this, up to disjoint unions. It's this SL2 example I gave in the beginning, and the dimension is 1. So we're going to have cohomology in degrees 0, 1, and 2, but we want to show cohomology in degree 2 vanishes as you go in the limit. And this is something that can definitely be done by hand. What I say, a lot of what I say will just apply verbatim to also, say, Siegel modular varieties, or, the Shimura varieties of Hodge type. So if you prefer, you can also think of those when I explain modular curves. So it's going to be, right, so the first thing is I take a perfectoid field. So I always want to work over some algebraically closed field, and in fact, I want to use p-adic geometry, so I'm going to look at the p-adic completion of an algebraic closure of QP. And because these, modular curves or Shimura varieties, so these modular curves have a model over Q, and so rather than thinking of them as complex analytic manifolds, I want to think of them as adic spaces in the sense of Huber. So I take the associated, so x gamma is the modular curve. I base change to this perfectoid field over QP. I take the associated adic space, and then I denote this by x star gamma. And one thing that I'm doing here, is that I'm going to take the minimal compactification. Okay, and the claim is that there exists a perfectoid space that's x gamma p infinity, right? So yes, that's true. For curves, there is only the minimal and the toroidal compactification agree. Sorry. I said that if you want to see the general proof, you can think they're not curves. So there exists a perfectoid space over C, which is perfectoid modular curve, which is characterized uniquely by the following property, that this perfectoid space is similar to the tower of adic spaces that you get by considering this level gamma p to the m and taking an inverse limit over m. So a priori, the inverse limit of adic space is not adic spaces, but is not necessarily an adic space. But what Schulze proves in his torsion paper is that there exists a perfectoid space, which is similar to this tower. And this relationship, I'd rather not define precisely here, but I'll just say that, so on the level of topological spaces, it's saying that the topological space of this perfectoid modular curve is homeomorphic to the inverse limit of the topological spaces of these adic modular curves. And on the level of structure sheaves, it says there is a cover by affinoid perfectoid spaces here, such that if you restrict to that cover, you have a dense image on the level of structure sheaves, where you take a direct limit over affinoids here. But this is a notion introduced in a paper of Schulze and Weinstein. So it's going to be enough to show that the cohomology with FP coefficients is 0. And so I'm only doing compactly supported, and I want it to be 0 for I greater than the middle degree. Okay, and so the first way to see this is this very general sort of abstract argument that was already in Helen's talk. So using perfectoid methods, the first way to see it is just, using so-called primitive comparison theorem in p-adic Hodge theory, and then using the fact that on affinoid perfectoid spaces, the cohomology of certain, say, coherent sheaves, the étale cohomology of certain sheaves such as O plus is almost zero above degree 0. But there is a subtlety that comes from looking at the boundaries, so I thought I would just quickly go through the sequence of comparisons. So the first way to see this is H tilde I compactly supported tensor over Fp with OC mod P. This can be identified with, well, okay, maybe I shouldn't say equal, but isomorphic with the limit over M of Hi et al. X compactly supported X gamma P to the M Fp tensor over Fp with OC mod P. So here I'm using sort of several comparison theorems between, say, singular cohomology and étale cohomology of schemes, and étale cohomology of adic spaces. And then at each finite level, you apply an isomorphism, which is sort of only in this almost category introduced by Foltings. So this is almost isomorphic to the direct limit over M of Hi et al. And I can look at the compactification, and with cohomology in a sheaf that I'm going to denote by I plus M. So I plus M is going to be sort of the subsheaf of O plus that consisting of sections that vanish along the boundary. And another way to define this is, so when I take the limit, this is in the almost category isomorphic to Hi et al. On this perfectoid space, I plus, and you can see that I plus is the same as J lower shriek of O plus on X gamma P infinity. So J lower shriek of this, sorry, mod P. I want to work mod P. This, where J is the open immersion of the modular curve, perfectoid modular curve, into its compactification.
Mod P also in the middle.
Yes, I have to take mod P in the middle. I'm just defining this the same way as being mod P. I've just defined this I plus as a mod P object, but I agree that, did I do something?
You said that this is the ideal O plus.
Yes, you're right, yes, I said this, I didn't.
No, it's not exactly.
Yes, you're right, sorry, I said this, I didn't write it, but yes, I do want to take mod P. It's just defined analogously. And I guess what I want to say here is that this is the primitive comparison theorem in p-adic Hodge theory, which in the case of schemes goes back to Foltings, and the specific isomorphism, almost isomorphism that I'm using is due to Scholze, and in his 2013 p-adic Hodge theory paper, he proved something like this for proper smooth rigid analytic varieties with the sheaf O plus, mod P. But so the specific one that I'm using is in a survey article that appeared in 2012 on current developments in math. So that kind of extends it to certain sheaves on proper but not necessarily smooth rigid analytic spaces. So one thing to emphasize is that this does need properness. So if you tried to prove this theorem for usual cohomology, you would still have to look at the compactification and take, say, R J lower star instead of J lower shriek. Okay, so that's maybe one thing. And then what you want to show, well, it's enough to show that this is almost 0 above the middle degree. And this, there's the one-line proof. Okay, I think this is right. There's the one-line proof which says that you can replace, so this is still étale cohomology, but you can replace étale cohomology with analytic cohomology because, so when you work in the almost category, because on affinoid perfectoid spaces you can sort of write down just an affinoid perfectoid cover of this, and on affinoid perfectoid spaces, HI et al. Of the restriction of this sheaf will end up vanishing above degree 0. And one thing that needs properness, and there's one more technical condition that allows you to work with I plus instead of O plus, which is that the boundary is so-called strongly Zariski closed. So the boundary x star gamma p infinity minus x gamma p infinity is strongly Zariski closed. And what this means is that locally, on an affinoid perfectoid cover, you have the corresponding map on rings that defines the boundary, and you want the map on the plus rings to be almost surjective. Not just the map on rings to be surjective, but you want the map on plus rings to be almost surjective. This is also a notion defined in Schultz's paper where he proves that in the case of these Shimura varieties, the boundary is strongly Zariski closed. And this is a condition that descends to affinoid subsets. Okay, but just a technical detail. This is almost 0, and this follows from, well, the fact that you can replace étale with analytic and then you use Scheider's result for locally spectral spaces. Have cohomological, say of dimension d, have cohomological dimension less than or equal to d. So locally spectral spaces are spaces that are locally homeomorphic to spectra of rings. And there's a sort of definition by properties, but yeah.
You need the spectra because it is just one.
Yes, that's right. Have cohomological dimension less than or equal to d. That's right. So this is spectral. It's just an inverse limit of spectral spaces is spectral. The reason I'm saying that Scheider proves this even for locally spectral space is that later we're going to consider a certain stratification, and there we won't necessarily know that it's spectral. Okay. So.
Oh, there is some technical hypothesis of the spectrum. I think that it should be.
I don't remember right now whether there is, but it will definitely apply to our situation. Right, so this is just the first way to see this, and the second, I want to give you a second way that's more involved, just to see star, because then it'll be easy to just sort of translate that to this partial level that we're considering. Namely, we're going to use the Hodge-Tate period morphism, which is a morphism of adic spaces, high Hodge-Tate, to, well, in general, it's to a flag variety. In the case of modular curves, the flag variety is just the adic space attached to, associated to P1. So you have something like this, x star, gamma, Right, X star, yeah, X star. So the perfectoid modular curve covers this finite level object, and once you're here, there's a morphism of adic spaces to this flag variety, which is the Hodge-Tate period morphism, and which measures the relative position of the Hodge-Tate filtration. So now I'm sort of really being specific in the case of modular curves, but there is a version of this for Shimura varieties of Hodge type. So just to give you a sense of what this does, so I want to forget about the compactification, and I just want to look at, say, COC points. Here, at finite level, what you're parametrizing are elliptic curves over C together with some gamma level structure. And here, you're parametrizing the same elliptic curve with a gamma level structure, but you're also parametrizing a trivialization of the Tate module of the elliptic curve. So an isomorphism with ZP squared. And then on the level of points, you can define the Hodge-Tate period morphism as sending such a tuple to Li of E twisted by 1 inside Tate module of the elliptic curve tensor over ZP with C, which under beta tensor 1 is isomorphic to C squared. So you will have, so Li of E, well, it's just a Tate twist, tensor over C, with C twisted by 1. So you have a one-dimensional C vector space inside this two-dimensional one. This is going to define a C point of this flag variety.
Can I ask?
Yeah.
In the top, when you're in the top degree, in any case,
Yeah.
the top dimension, like 2D,
Yeah.
so for modular curves 2, is it always just multiplying by the degree of the map? I mean, what I'm trying to say is this kind of, the whole thing kind of a little bit obvious.
Yes, I agree. Yes.
Modular curve, like this thing, it's just you're multiplying by P.
Discuss that.
Yeah, I think so.
She wants to show the method, but in some cases,
Yeah. No, but I just wanted to make absolutely sure that I didn't.
Yeah. The modular curves you can do by hand.
You know, like, that I'm on.
Okay, so what's happening now is that we can use the Leray spectral sequence for the following morphism of sites to compute the cohomology at the top. So the cohomology at the top of this I plus is what we want to consider, and we will use the Leray spectral sequence for the morphism of sites. For pi Hodge-Tate that goes from X star gamma p infinity, and I want to look at the Étale site of that and go just to the underlying topological space, the analytic site on P1. And so this just goes by looking at the underlying, so you go via the underlying topological space for the perfectoid modular curve. And then you have two ingredients. One is Scheiderer, which we will use for P1. It's the last one, but the first one is roughly that the fibers of pi Hodge-Tate are aphanoid perfectoid.
Because this is defined on the compactification.
Sorry?
Is it defined on the compactification?
The Hodge-Tate period map, yes, it's defined over the compactification. There's a slight subtlety for Shimura varieties of Hodge type, but it does not affect Étale cohomology. So I can tell you about it later, but other than this slight subtlety, it does extend, and it's essentially by continuity. Aphanoid perfectoid. So what this means, and for this to be true, you do actually have to look at the compactification. What this means is that, well, if I have X, say, a rank 1 point, So SPA K, I mean, I can reduce the computation just to rank understanding the stalks over rank 1 points. And over a rank 1 point like this, where K is a perfectoid field, I can write X as an inverse limit of certain rational neighborhoods of X. U, so in fact, over P1, I can use the standard cover of P1 into by 2 copies of A1. And I can look at, so it turns out that the preimages of those 2 copies are going to be aphanoid perfectoid. Are going to be aphanoid perfectoid, so also for any rational subset contained in there, you have aphanoid perfectoid preimages, and then X is going to be the inverse limit of such things, and the stalk R pi Hodge Tate lower star, where, okay, so maybe I want to say pi Hodge Tate, I'll put it in brackets to denote this morphism of sites. I plus, if I take the stalk of this at X, turns out this is going to be the direct limit over U of HI et al. So direct limit over U, HI et al. Pi Hodge Tate inverse of U, and then the restriction of I plus. So again, because you have an aphanoid perfectoid space, this is going to be almost equal to 0. And that's what allows you to conclude. So this, I'll say, equals almost 0 for I greater than 0. So this is the first ingredient. The second ingredient is again Scheiderer for P1, which tells you it has cohomological dimension at most 1. So what happens when you go to the partial tower is that the fibers are no longer aphanoid perfectoid. So for theorem 2, you're looking at what we end up looking at is the morphism of sites that's obtained by taking a quotient under the ZP points of the unipotent. So in this case of modular curves, I take n to be 1, ZP 0, 1, and I consider the morphism of sites pi Hodge Tate mod n that goes from, X star gamma 1 P infinity. Now, this isn't a perfectoid space. If you want to make sense of this, you can define it as the inverse limit of the corresponding finite level things, but then it doesn't necessarily exist as an adic space. To make it precise, you need to work in Schulz's category of diamonds. But in any case, so this, the underlying topological space, so I take the et al. Site, I just look at topological site, gamma 1 P infinity. This turns out to be homeomorphic to X star gamma P infinity mod n, and then this maps down to P1 add mod n. And I just look at the underlying topological space, and the morphism of sites that I want to consider is this composition. And one thing that I should say here about this Hodge-Tate period morphism that I forgot to say, but that's very important, is that it is equivariant for the GQP action. So you have an action of GQP at the top. You can, for instance, already see this kind of on the level of complex on the level of locally symmetric spaces. And you also have a natural action. In this case, GQP is GL2, or SL2QP has a natural action on this flag variety. That also generalizes. And so I think of N as a subgroup inside GQP, and I take the quotient, just as a topological space. Okay, and then in the last minute, I just want to draw the picture and tell you what happens. So we're going to, again, use the Leray spectral sequence for this morphism of sites. So we're left with understanding Ri pi Hodge Tate mod n lower star of I plus. This is what we want to compute on P1 mod. And what does P1 look like? This is a rough picture. So this is point infinity, which I can think of as, say, coordinates 1, 0. I call this the canonical point. And everything else is the non-canonical locus. Inside of it, you have some open subset that's the so-called anti-canonical locus. I'll explain these names, but first I want to draw the picture. So there's an action of GQP. In particular, there's an action of the element, say, P00, P inverse in GQP. What this does is this expands the so-called anti-canonical locus towards, so to cover in the limit the whole non-canonical locus. It never covers the canonical point, but otherwise it does. And there's also an action of a Weil group element, or representative of a Weil group element, which exchanges 1, 0 with the point 0, 1, which is contained inside the anti-canonical locus. Okay, so this is the picture, and now the point is that the fibers over the non-canonical locus are always affinoid perfectoid spaces, even at this level gamma 1 p infinity. But the fiber over the canonical point is no longer affinoid perfectoid. So that's why the proof from there doesn't apply. But sort of what happens if you look at the special fiber of the modular curve, so you look at level gamma, you have the ordinary locus, supersingular points. Let's say gamma is tame, so prime to p. If you go up to level gamma 0 p, maybe I'll draw the special fiber, x gamma, so supersingular points, ordinary locus. If you go to gamma 0 p, you have two components, two irreducible components that, well, meet at the supersingular points. It's a normal crossing divisor. The forgetful map that goes from this level to this level on the special fiber, on one component it's an isomorphism, on the other component it's the relative Frobenius. So you study this on, say, the gamma 0 p infinity tower. This is what Schulze does to prove that Shimura varieties or modular curves do get this perfectoid structure in the limit. On the gamma 0 p infinity tower, there's going to be a part of the tower that is going to become perfectoid early on. And if you include the compactification, even affinoid perfectoid, and there's going to be a part of the tower where the transition morphisms are just isomorphisms. So that has no chance of becoming perfectoid at this level gamma 0 p infinity. But so the upshot of studying this is that you can show that, so the fibers of pi Hodge Tate mod n over P1 add minus the point infinity are affinoid perfectoid, and the fiber over the canonical point is not, but it actually, if you go to a full infinite level, it does. So the fiber over infinity has a ZP cover, which I put in quote marks because it's a torsor on the open part, but not in general. Has a ZP cover, which is affinoid perfectoid. Because that ZP cover you see by going to infinite level and using this Weil group element. So the group cohomology of ZP tells you that cohomological dimension over this point is 0 and 1. Cohomological dimension here is just 0. And if you analyze the Leray spectral sequence, you get the desired vanishing theorem. And you can generalize this by studying the Bruhat decomposition on a general flag variety for Shimura varieties of Hodge type. So I'll stop here. Sorry.